If you want to learn Pixar's universal scene description, specifically the USD physics schema, or you want to learn Nvidia PhysX, or you want to understand how they work together, this is the video for you. Okay, so what is this video all about? Okay, it's about OpenUSD Physics and PhysX physics. Now, what exactly is that? So here's a nice little simple description given by ChatGPT. So OpenUSD is a powerful framework for describing 3D scenes, including physics properties, which is what we're going to be focusing on, but it doesn't simulate anything. It's just a specification. Nvidia PhysX is the engine that reads those descriptions and brings it to life. There are other engines, but I'm focusing on PhysX. So if we look at it in a little bit more detail, here we've actually got a table to compare. And when we're talking about physics, we're talking about things like rigid bodies and body mass properties and collisions and materials and collision groups and joints and that kind of thing. So let's look at the table here. OpenUSD is a scene description framework and the physics is the simulation engine. And the purpose of OpenUSD is to describe what's in the scene. And the purpose of PhysX is to actually calculate how those objects will behave under the physics laws. And what is OpenUSD? It's a specification and a data model developed by Pixar. And PhysX is a software library developed by Nvidia. And the role here, it stores the metadata about mass and density and frictions and joints, etc. in a structured manner. And PhysX actually simulates the motion and the collision and the forces using those parameters. And the file format is USD, USDA, USDC, and USDZ. And PhysX is not a file format. It uses those file formats, and it's the engine that runs it. And lastly here, how they work together. So USD describes the physical world, and then PhysX interprets and simulates it. So PhysX relies on the structure that we create with OpenUSD and the metadata that's stored in there, and then it uses that to actually do the simulations. And what I've done is I've created a repo that I'm using, and the purpose of this is for me to understand it all better. And I've started sort of on a staged approach. Each video is going to get more and more in detail. But if we look at what I'm starting with here, starting with rigid bodies, kinematic bodies, body mass properties, collision materials, collision groups, and finally joints. And in case you'd like to look at the underlying references that I'm using as I work through this, you can go to openusd.org and you can get an idea of on the main page here exactly what it is. I'm specifically looking here at the USD physics schema, and you can see we've got things like, as I mentioned, rigid bodies, kinematic bodies, collisions, joints, etc. On the PhysX side, Nvidia Omniverse, github.io, we've got the PhysX counterpart to all of that. Again, very similar things. We've got rigid body, joints, and between these two documents, I'm going through in a staged manner, understanding the basics, and I'll be working deeper and deeper to understand more and more complex concepts and put each of those into the videos as we progress. And I will leave links to these two documents in the notes on this video in case you want to dive into them. And each of these is a video of these items in action. So we're going to see the specification in USD. We're then going to go into Isaac Sim, and we're going to use the simulator where we take those specifications and we see each of these things in action. So it's going to be very visual. And as I've said, I'm starting with the basics and I'm going to dive deeper and deeper in each episode. I'm imagining, although this is quite a long video, probably close to 40 minutes, they're going to be 5 or 10. And I will get some of this wrong because I'm busy learning. So please use the comments to correct me and I can correct it in the later videos and we get a conversation going. And once I'm done with the series, I will clean up and publish the repo. All right, so let's jump right in. Okay, so we're going to start off with rigid body. Let's close this and make a bit of space. So before a rigid body is added, we've added a cube and we can see these are the property for the cube. So let's watch the video now of adding the rigid body. So we can see if we push play and we can see here's me running the simulation and there is no gravity being applied to the cube. So we're going to go add physics, rigid body, and we can see now when we push play and run the simulation, gravity is being applied. So let's look at the code that's created that. We can see two API schemas have been prepended. So it's the physics rigid body API, which is the OpenUSD schema, and then the PhysX rigid body API is the PhysX schema. And we can see two other properties, so we can ignore the kinematic enabled. We'll come to that a little bit later. But the rigid body enabled is true, and that is what makes it fall with gravity. So let's move now and add linear velocity. So we can see when that cube fell, it didn't have any other movement except the gravity pushing it downwards. But let's say we wanted it to be moving in a specific direction as it starts to fall. So let's see how we'll do that. So let's push play here. And we're going to see here, I'm going to linear velocity on the X, so it'll move along the X, and we'll put that at 2. And we'll see when we push play, not only does it fall with gravity, but it's already moving at the speed that we specify on the X. All right, so let's see the code, and we can see it's just this extra property here, which is velocity, which is the linear velocity, and on the X-axis is 2. Now, if we want to add angular velocity, meaning it'll be spinning, let's see how we do that. So I'm going to push play. And what you're going to see is below the linear velocity, I'm now going to go to the y-axis, and I'm going to add a 100 value to the angular velocity. And we can see now it actually starts to spin. So in addition to moving linearly and moving with gravity, it is spinning. And let's look at the code it generates to do that. It adds this extra property, angular velocity, and on the axis we've added it. Now, bodies can also specify a simulation owner. So if there are multiple scenes, each scene will, let's say, for example, have a gravity. So here I'm going to show you a video where we've got default gravity on the one scene, and we've got a much lower gravity set for the second scene. And then depending on which scene we specify as the owner of the object will fall according to the gravity of that scene. So let's push play here. And we can see, let's just open up the layers here, and we can see under physics scene 1, and we pull up a little bit, we can see the gravity magnitude is Earth gravity, which is just under 10. And for physics scene 2, gravity is 1, which is much, much lower. So we can see the simulation owner on this cube is physics scene 2, which is the much lower gravity. So if we simulate now, we're going to see it's going to fall really slowly. So there we go, it's falling, but that is much slower than Earth gravity. But if we go back in here and we reassign it to scene 1 with Earth gravity, we see it is going to fall at a much faster speed. So let's go ahead and remove the simulation owner and re-add it back as physics scene 1, which is Earth gravity. And then when we push simulate, it falls at a much faster speed. All right, so let's go ahead and look at the code that's generated for that. So we can see here we've got a property which is the simulation owner, and it's either physics scene 1 or 2. And then where we see the two scenes defined, scene 1 has no gravity set, so it'll default to Earth gravity, but scene 2 we have set it to a gravity. Well, in this code it's 2, although in the video it was 1, but you can see we can have different gravities, and then that object will fall according to the scene that it is assigned. Okay, next up is kinematic bodies. So let's give us a little bit more space here. So kinematic bodies are read-only X-forms as far as the simulator is concerned. Physics forces don't act on them, but they act on other bodies. So the animation system is actually what animates them and not the physics system. So for example, you would have seen in games where the player will control a character, and that character must do what the player is commanding via the keyboard, for example. And the other prims in the scene must be affected by the character, but not affect it. And let's just look at what happens when we put that property as on. So we can see we've got rigid body is enabled, and it reacts to gravity if we run the simulation. But if we enable kinematic and we run the simulation again, it now won't be affected by gravity. I will go into a more complicated example a little bit later on, but here we'll just see that when we set it to kinematic enabled 1, that is what happens. Okay, so now moving on to body mass properties. Let's make a bit of space here. So the mass API is separate to the rigid body API and isn't required, as you'll see in some of the examples below, where we can calculate mass from collision geometry or the material API. But let's go into some of the examples, and that'll make sense as we go through. So let's start with the first one, where density is assumed to be 1,000 kilograms per cubic meter. Let's click into that example there and push play. And we can see we've got a 1 by 1 by 1 cube. There's the size, 1 meter. And if we hover over the mass, we can see it is 1,000 kilograms. Now let's go into the next one, which is mass is assumed to be 1 if none is set and no colliders. So we haven't added a collider and we haven't added any mass, but we have added a rigid body. And as we hover over there, we can see the mass is 1. Now that might be a little bit confusing in that you're wondering why, if it's a 1 by 1 by 1 meter cube, why is it not 1000? That's because it just defaults to the 1, and only once you add a collider, which actually gives a way of calculating the volume, will it calculate the correct mass. So what you're seeing here is before we actually have the volume, all it does is it takes the size, and because it's 1, it times is 1 by 1 by 1, which still gives us 1. Okay, now on to the next one. Parent's explicit total mass takes precedence. So let's see that in action. Okay, so we can see we've got a parent X form, and that has a mass of 17.58. And it has 2 child cubes. Okay, let's go and add mass to the first cube. And let's set that mass. Okay, that mass has been set to 20. And we're going to do the same for shape 1. And we're going to add mass to it. And we're going to set that to 10. And we can see now that the total mass is 30 because it adds those two together. But if we go there and explicitly add the mass to the parent, and we set that at 15, we see that is overridden, and that becomes the total mass. Okay, moving on to the next one. Density has lower precedence than explicit mass. Let's click into that video. And again, we can just confirming here that we've got our units as 1 meter per unit and 1 kilogram per unit. And there, if we look at 1 by 1 by 1, should give us 1000 kilogram mass. So we've added a cube. And we're going to add a rigid body, mass, and a collider. And we can see if we hover over, it gives us 1000 kilograms as expected. Okay, so to further illustrate that, let's just duplicate that cube. And we're going to set the size to 2. And if we look at the calculation, that should give us 2 by 2 by 2, which is 8000 kilograms. And we hover over and we see it does give us 8000 kilograms. But if we go and assign a mass, it'll override that calculation it's done. So let's go into the mass property specifically, and we change it to 5000. And we can see that value overrides the other calculation. Okay, moving on to the next one. Child density overrides parent density. And let's see that in action. Parent X-form density is 1. And we can see there it's set as 1. And if we look at the child, the cube itself, its density is also 1. And the child box is 2 by 2 by 2, which should give us a mass of 8. So let's go ahead and look at that. If we look at the parent X form, our mass is 8. And then just so as not to confuse things, we can see it's not 8000 because we haven't added a collider. So it's not doing the full volume calculation. It's just multiplying the size by the density. So let's see what happens now. If we adjust the parent's density to 2, we will see the mass remains at 8. But if we adjust the child's density to 2, that then takes effect. And we'll see the mass then goes to 16. So the child's density overrides the parent's density. Okay, let's move on to the next one. The mass API density overrides the material API density. So let's see that in action. So we again have got a cube of 2 by 2 by 2, density set to 2, so the total mass is 16. So we can see their density is 2 of the child. and we hover over on the X form, and we see the total mass is 16. And that's because the applied material has a density of 3. We can see the applied material has a density of 3. That test material, density of 3. But the density from the mass API overrides that, so it remains at 16. But if we remove the mass API value, then it'll jump to 24 because it'll take the material's density. So we're going there to the density setting, and we're going to remove that. And we'll see now it will take the density of the test material, and it jumps the mass up to 24. And lastly, implicit mass is collision geometry times density. Before I push play, I'm just going to explain what is happening here. So we've got a mesh cone on the left, and we've got our cube on the right. And our cone has a collision mesh added to it. But there are various different ways that that collision shape and mesh can be calculated. They are what are called approximations. So you can see here, before I push play, there's what type of approximation are we using. And in this case, we're using a convex hull, which creates a shape very close to what the cone looks like. But we can also create a bounding cube and various other different approximations, which will create a different shape around the object, and depending on the complexity of the object, that shape might approximate the object or might be quite different. So you'll see when we add a bounding cube, it's going to actually add just a cube that encompasses this whole area. And because the volume is based on the approximation that we used, it creates a very, very different volume calculation. So just let's look at this in action, and I might stop it along the way to explain. So we can see here, just noting there that the computed volume is collision geometry times density. And if we use the convex hull, we get 262 kilograms, which is about accurate there. So convex hull, and we hover over there and we see 262 kilograms. But if we use the bounding cube, and I'm just going to change that setting. So we go to the approximation, we change bounding cube. You see it creates this cube. I'm just going to pause here. So it creates this cube around the cone, which is 997 kilograms, which is literally like if we had a cube of 1 by 1 by 1, it would be 1,000 kilograms. So we can see it's almost 1,000 kilograms there. And you can see, depending on the approximation, it creates a very different volume. And it's worth going through the various different approximations. There's 7 or 8 of them, and each one has a different formula that it creates the collision mesh around. Some are more intensive on the GPU to calculate, and others are easier. So obviously a bounding cube will be a lot easier than some of the others, but they don't give us an accurate volume calculation. So let's go ahead and just run this. So we can see that I'm just highlighting the implicit mass is based on the collision geometry and not the actual geometry. So we can see the actual geometry of this cone is different to the collision geometry depending on which collision geometry we have selected. But setting the mass explicitly will override this. Okay, so let's move along to collision. For simple USD prims like sphere, cylinder, cube, and so on that are not mesh prims, we just add these two schemas, PhysX Collision API and PhysX Collision API. And let's have a look at this in action. Let's go ahead and create a cube. And we're going to save this file so we can see the USD that's been created for that. Okay, let's pull that up. And we can see our cube has been defined. Now we're going to add a collider, and let's see what it adds there. So we click on our cube, add PhysX collider, and save. And we can see it's added those two API schemas. And that's the same for all of the other simple shapes, capsule through to sphere. Now we'll move on to mesh prims, which are a little bit more complex. So for a mesh prim, in addition to those previous APIs, the mesh collision API is also added. And then there's a PhysX API as well. So we've got the PhysX mesh collision API on the USD side. And then on PhysX side, there's the PhysX triangle mesh collision API. And then along with that, an approximation will be set. So let's see what that looks like. Here we can see we've got 3 mesh prims. Let's start with the cone, and we can see it has a collider. So there are multiple approximations to choose from for the collider, and you'll see how each one affects the collision geometry around the object. So there is the triangle mesh, convex decomposition, and so on. As we're going through each of the approximations, you see each one has a different box it creates, or a different geometry it creates around the prim, which will act as the collider, which you'll see in a moment. And then we will demo that with a torus, which makes it a little bit more obvious. So you can see, let's set that to triangle mesh. Okay, sorry, triangle mesh won't work there. And we'll set that to convex decomposition, and then let us simulate, and we'll see it hits the floor there, and then it stops it where the collision mesh is defined. But then if we add a bounding sphere, you can see the collision mesh actually is a full sphere around the torus, and it extends beyond the actual torus itself. So we'll see when we run the simulation, that bounding sphere will act as the collision matrix, and it will stop at the edge of that bounding sphere and not at the edge of the torus itself. Let's see that. And there we can see that in action. And then let's look at our USDA file. And we can see those extra API schemas have been added, those 2 at the end there, in addition to the original 2 for the non-mesh objects. And we can see we've got an approximation set, and that's just not showing because we haven't saved it. Let's go ahead and save the work we've done there, and then we'll see, yeah, there we go. It's showing as convex hull. Okay, so moving on to material. There will be 4 different descriptors, starting with static friction. So that's how much force is needed to start moving the object from rest. And as an example, if you had 2 boxes on the floor, one with a lot of friction and one with very little friction, if you kicked the one with a lot of friction, it would hardly move. And if you kicked the one with very little friction, it would move a lot more. So let's just see that as an example. So we've got 4 boxes here. I'll explain what each of them are for. Let's just start with the 2 materials. So physics material 1 has a static friction of 0.1, which is low, and then physics material 2 has a static friction of 6, which is a lot higher than that. And we can see we have 2 cubes, cube 1 and 2, and those are assigned to both material 1 and material 2. So we'll see cube 1, if we hit against it, it will not resist a lot and it should go sliding, and cube 2 will hardly move at all. And we have our 2 cubes behind, cube 101 and cube 201, which have some existing linear velocity. And as we run the simulation, we'll see those will hit into the cubes, and we'll see that static friction in play, where one cube will move a lot further than the other. Let's see that now. And there we go. Next is dynamic friction, which is how much resistance the object has when sliding if it already has some motion in it. Imagine if you throw a box with a lot of friction, as it hits the floor, it will stop very quickly. And if you throw another box with a very little friction, as it hits the floor, it will slide along quite a ways. So let's see that in action. And let's see our 2 physics materials. We have a dynamic friction of 0.1 on the first one and a dynamic friction of 0.9 on the second. So that's a lot more friction. And both of those boxes are set up with a linear velocity. So we'll see as we run the simulation, they're going to both shoot forward. And as they hit the floor, there will be a different amount of friction that causes the one to stop a lot earlier than the other. So let's see that. And there you see the one slides way more than the other. Okay, moving on to the next property, and that is restitution, or how bouncy something is. So let's see that in action. We can see we've got 2 physics materials. One of them, the restitution is 0.1, and the other, the restitution is 0.9. And we'll see as we run the simulation, they will both hit the floor, and the one will hardly bounce at all, and the other will bounce quite a bit. And there you see the one is bouncing way more than the other one. And finally is density. And we've had quite a few examples of this a little bit earlier on, but let's just see a little bit more explicitly how that's set. So we've got our 2 materials, one with a density of 1, and the other with a density of 5. And we assign each of those materials to the cubes, and then if we go and look at the cube's mass, we can see it is reflected based on the material. So we hover over cube 1, shows us a mass of 1, and we hover over cube 2, and it shows us a mass of 5 based on the material. Okay, moving on to physics collision groups. So let's just imagine a very simple real world example. We've got a character, which is under world character, and we've got a cloth object, which is under world cape. So this is the character's cape, and we've got a wall, and we want the character and the cape to collide into the wall, but not to collide into each other. So what you could do, we could assign the character and the cape into different groups, and then we add each other to the other's filtered group list. So we're going to watch a little video of this in action. Again, what you're going to see here is the character avoids the cape avoids the character, but both the character and the cape will collide into the wall. So we see this in action here, and we can just see like a very rudimentary version of this is our character, this is the character's cape, and this is the wall. So if we run that, we'll see as it's simulated, the character and the cape are not colliding with each other. And we can see there we've got the cape, the character, and the wall on the right, and then we've got three collision groups. So character, cape group, and environment group, which is the wall. And we see if we take the cape and we throw that into the wall, it stops. So it does collide against the wall. And if we take the character, that also collides against the wall. But we see they did not collide against each other. And here, let's look at the code. So we can see collision groups. We've got our character group, we've got our cape group, and we've got our environment group. And we can see under the character group, the filtered groups is cape group, so it will not collide. And under the cape group, the filtered groups is character group, so it will not collide with that. Whereas the environment group has no filtered groups, so both of those will collide into the environment, which is the wall. Okay, now we'll move on to joints. Let's give ourselves some space here. So we'll start with a D6 joint, and the reason I want to do that is if we can understand all the characteristics of the D6 joint, it'll allow us to actually build some of the other joints and understand how they work under the hood. So let's start with this D6 one, and then the others should make a lot more sense. So the D6 is called the D6 because it has 6 degrees of freedom, the trans X, Y, and Z, and the rotation X, Y, and Z. So as an example, we're going to create a joint with all 6 degrees locked. So the two objects are connected, but there will be no movement. And then we will build from there. So let's have a look at what that looks like. We go ahead and run it. So there's just a bit of an explanation, 6 degrees of freedom and translation XYZ and rotation XYZ. So we're going to go to the physics examples, and we're going to go to the D6 joint. And we can see here we've got a little bit of a utility to allow us to lock or unlock any of those axes. And here I've locked them all basically. So we've loaded the scene, and they have been added automatically with this UI, but we could add them manually, and I'll show you how to do that in a second. And we can see if we scroll down, we've got all of our limits. So X, Y, and Z on rotation, and the X, Y, and Z on translation as well. And here's just a way in which we can add it manually. So if we delete one of those, we could say add limit and Z axis translation, and it comes back. So we could add all 6 of those manually, or we can just use this utility. And by default, each is locked by adding a range that's not possible. So 1 is the low and -1 is the high. There's no movement with that. There we go. There's the low limit of 1 and the high of -1. So we can see that's no movement at all. So if we run the simulation, we'll see what happens. We push shift and drag it, and we can see nothing happens at all. Normally that will make some kind of movement happen, but because it's totally locked, as we're clicking on it and dragging, it's not moving at all. And here's the code for the joint. So we can see it's given us prepended several API schemas, and one for each of the axes at the top here. And then it has put the high and low for each of those. There we go. So now let's start looking at each of the axes. Let's go to translation X and see what happens if we set some usable limits on that. So we'll click on that, and then let's run the video. So we're adding a translation X here to the D6 joint. So we'll scroll down here and we'll find X translation, and we'll put -50. And on the high limit, we'll put +50. And we can see already in the UI, it's showing us in which direction. So we're going to see it's going to go across here, and that lines up here with our X axis. So if we run the simulation and we push shift and pull it across, we can see it moves across our X axis nicely. And we can see here our code, it's modified the code above just slightly. All that we've done is we've set these two lines, whereas before they were -1 and 1, we've now got 50 and -50. And that achieves what we just saw in the video. So now let's move down to the next degree of freedom, which is the Y, and let's see how that looks. So run the video. We're going to do exactly the same thing. We're just going to do that on translation Y. And again, we're going to go -50 and +50. And we can see now that's going to allow us to move along that axis, which is the Y-axis here. And in the simulation, it gives us something similar to a prismatic joint. All right, moving on to the Z-axis, so translation Z, and let's watch the video for that. Set it with -50 and +50, and in the UI it shows us that's going to be a vertical axis it can move along. Again, the Z-axis here lines up with that. And if we simulate it, there we go. All right, so let's move on to rotation now. Let's start with rotation X. And once again, setting it to -50 and +50. And we can see that is our range we're going to get. And we simulate. And that's what that looks like in action. Moving along to the rotation Y. Let's run the video. And we've set -50 and 50. And we can see now that's going to rotate along the Y. A little bit more difficult to see because it's only a slight movement, but let's zoom in and see. There we go. That's our Y rotation. And lastly, let's move on to Z rotation. There we go, -50 and 50, and we see that is what we're going to get. And let's simulate that and exactly what we expect. Now let's move on to unlocking two axes at the same time. So here we're going to unlock X and Y translation. So let's have a look at how that works. So we're going to set the X to -50 and 50 and the Y to -50 and 50. And there we see we get our 2 degrees of motion that way and that way. We can see we can move it across that way and in a prismatic way as well. Let's just change our perspective a bit to see a bit better. There we go. It can go forward and sideways. Okay, and then let's look at unlocking two rotations, the rotation X and Z. So there's the X rotation to -50 and 50 and the Z rotation to -50 and 50. And we see that's exactly what it's going to give us. And how does that look in simulation? There we go, exactly what we would expect. All right, so now that we've looked at the 6 degrees of freedom that we can work with and set individually or together, I think we can look at each of the these joints following, the prismatic, revolute, and spherical, and we can try and build those from the ground up. Once we've understood each joint and recreated it, we can then build the same thing with the D6 to understand how it works under the hood. So let's start with prismatic. And we're going to load the sample that comes with PhysX Sim. And that's what we would expect, prismatic to open like a bit of a drawer or a sliding rail. Okay, so what we're going to do now is we are going to delete the joint and re-add it back. So we can see how to do that. And then we'll go on to recreating it with the D6. Okay, so we have deleted it. And then we will just select both objects, both cubes. And there are a few ways of adding it. We go create PhysX joint, and we could go to prismatic joint there, or we could also do it on the top left, PhysX joint prismatic there. Or what I'm going to do to actually add it is you just click on the actual objects in the UI, create PhysX joint prismatic. There we go. Now it's added the joint. I'm going to have to align it a little bit and set some limits. So at the moment we see it's not limited as far as upper and lower limits, and we see if we run it, it's actually going along the x-axis, which is not what we want. And if we look there, we actually want it to go along the y-axis. So we will scroll down, and we will scroll down to the prismatic joint and select the y as the axis. And we see we haven't set any limits, so look what will happen. If we drag it, it's just going to head off into nowhere and it won't stop at all. It'll go on indefinitely. So let's give it some limits. Let's stick with our normal minus 50 and 50. And then let's just move the center of the joint to between the two objects so it works properly. And then we run it. And now it's doing what it was doing when we first loaded the sample. Okay, so now it's time to recreate this with the D6 joint. So we are going to duplicate our cubes. So let's select both of those cubes and right click and duplicate, and then drag those off to the side. And then it will have duplicated the joint as well. So let's delete that. And now we're going to add our D6 joint. So let's select both of those boxes. And again, create, physics, joint, D6 joint. And we will move the center point to between the two objects to our y-axis translation and do minus 50 and 50, which should give us exactly what we have in our prismatic joint. And we can see if we do that, the prismatic joint does exactly the same thing as the D6 with that specific axis unlocked. So let's go ahead and look at the code for this file and see how USD has specified this. So we can see under the prismatic joint, that is the definition for the prismatic joint. And really the main thing set there is minus 50 and 50. And then if we look at the D6 joint, we can see it's got all the limits like we see before, but only two of them have been set, the upper and lower, on the translation Y. Okay, so let's move on to the revolute joint now and do exactly the same thing. And once again, we're going to load the revolute joint from the samples. And let's see how that works out the box. Okay, we can see it's revolving around the x-axis. And we can shift and drag it down along that axis. Okay, so we're going to delete the joint and add it back again. So select and delete. And now let's select our two objects and right click, create, physics, joint, revolute joint. And then let's move it between the two objects. And we can see at the moment it's not limited, so it goes all the way around, whereas before it was a bit limited. So let me just try and grab it here with a shift. Kind of difficult while it's moving. Ah, there we go. Now we can spin it around on its x-axis all the way around. And we can also go and set it like it was originally with a limit on it. So 50 and 50. There we go. So it's now limited. All right, so time to replicate this with our D6 joint so we understand it. So let's select our two objects and duplicate them. And drag them off to the side. And let's just remove that joint that it would have copied as well. Let's delete that revolute joint. And let's select our two objects and add a D6 joint. There we go, there's our D6 joint, and let's move the center of the joint between the two objects. We will find the x-axis rotation and add in our minus 50 limit and our plus 50 limit. And now we've got both joints doing exactly the same thing. Our revolute joint and our D6 set up to behave like a revolute joint. And let's look at our code. And we can see our revolute joint defined there with our lower and upper limit. And let's look for our D6. And it's pretty much like we saw in the previous example, except rotation X, high and low, have been set in this one. And let's move on finally to the spherical joint. And I actually didn't give a definition for each of those. So prismatic, the joint supports linear along a single axis, like a slider or a drawer rail, as we've seen. Revolute supports rotational, like a wheel, as we've seen. And finally, the spherical joint supports a cone limit, like a human hip, which we're about to see now. So let's go in there. And once again, we will load it from the samples in Isaac Sim. And if we click on the joint, we get an idea of its range of motion. And if we simulate, we see it spins around almost like we can imagine a hip would. So it works on 3 axes. So now we'll go ahead and delete that joint and select both cubes and create physics joint spherical and move that to the middle between both objects. and we will select the y-axis, and we will have the cone angle limit at 45 on both of the other axes, and we should pretty much have the joint we started with. So let's go ahead now and duplicate that with a D6. So duplicate and move our objects across. Now we will delete our copied spherical joint. Now let's highlight both objects, right click, create, PhysX, joint, D6, and let's put the center between both objects. Okay, there we go. And under the X rotation, we're going to put in -25 and a high of +25. Y rotation, we're going to do the same thing. And Z rotation, we will also do the same thing. And this will give us pretty much what we see with a spherical joint. Not identical, but pretty close. And let's have a look at our code. And if we look at our spherical joint here, we will see that is our definition for the spherical joint. And we will see specifically the 45-degree for both cone angles, and the axis is the Y. And if we look at our D6 joint, we can see this one's a little different than the others in that we have set 3 different rotations with its high and low. Okay, so that's all for now. Thanks for watching and see you in the next one.